Hello, welcome to Einstein's Mechanics. In today's episode, we are going to solve one problem under power transmission of a shaft. So, without wasting much time, please subscribe to the channel, like and drop your comments. Determine the maximum allowable power which can be transmitted by 150 mm diameter shaft, which is running at 240 revolution per minute when the permissible shear stress is 50 Newton per mm square. So this is a problem we have. So we can write down our parameters that the diameter given is 150 mm. So that is going to be 0.15 meters. It is also running at 240 rpm, so which is the number of rotation of the shaft per minute, and that is 240 rpm. So for every minute the shaft is going to rotate 240 times. Also, we are giving the permissible shear stress. So shear stress is giving us 50 Newton per mm square, which is the same as 50 megapascal. So we are to find the allowable power transmitted, which is our P, is what we are looking for. Are we okay? So right away, let's look at the relation that is going to help us to calculate for this. Now, we know that the power transmitted by a rotating shaft is going to be T omega, and from here we are able to deduce that the power is going to be 2 pi n T on 60. So when we look at this place, we have the parameters, but we don't have the torque given, right? So we have to use an expression to find the torque of the shaft. So here we also have a relation, say torque on J is equal to the shear on the radius. Are we okay? So from here we can say that torque is equal to now the shear on J divided by the radius. Do we have the parameters? Yes. We also know that J for a shaft, this is a solid shaft, that is going to be pi on 32 d4. So we can put it in and get our torque to be, let's work in terms of mm. So the shear is 50 multiplying J, which is pi on 32. The diameter, which is in terms of mm, 150 raised to the power 4. Everything on radius. So if the diameter is 150, then the radius is going to be 75 mm. So that is going to be divided by 75 mm. So with this, we are going to have our torque to be 331,339,85.02 mm. We can transmit or transfer this to meters. That is going to be divided by what? 1000, right? So that is going to give us 3.9. We can run to be what? 9. So we move 1, 2, 3, and we are bringing it here. So this is in terms of Newton. So Newton dot meter for the torque. All right. So now that we have our torque, we can bring it back into the power equation and get the power transmitted. And remember, power is in its standard unit, which is watt. So we have to use the meter of the torque, right? All right. So here our power is going to be 2 pi. What is n? Which is the number of revolution. That is 240 multiplying the torque, which is 3.99. Everything on 60. So right from here, if you punch, you are going to get your power to be equal to 832.7 kilowatts. Are we okay? Therefore, you can conclude that the allowable power which can be transmitted by the shafts is 832.7 kilowatts. That's very interesting. So this is it. Let's look at the next example. All right, so we have an example here where we are also to solve. It's a very simple one. Please pay attention so that you can understand. So the shaft shown has a coupling on it, which has 6 bolts on a 260 diameter pitch cycle or circle. Determine the diameter of the bolts if the maximum shear stress in the bolt must not exceed 100 Newton square and the power transmitted is 314 kilowatt at 500 RPM revolution per minute. So there's a shaft which is coupled. It is combined with 6 bolts. It's like we are fixing 6 bolts on a shaft. We have 6 of them of the bolts, and there is what we call pitch circle diameter. It is the circle, when we draw it, is going to pass through the center of these 6 bolts. So assuming we have these 6 bolts on a shaft, the diameter of the pitch circle is a circle drawn to pass through the diameter of all the 6 bolts. And we are saying that diameter or that circle is 260 mm. Now we are to determine the diameter of the bolt. That means the 6 bolts, assuming if they have the same diameter, we are to determine that. Given all these parameters, the shear, the power transmitted, and the revolution of the shaft, we can do that. So we have the parameters given. Are we okay? So solution, we are going to write down the parameters. So we can say number of bolts. We are given 6 of them. And we are also going to look at the, let me use pitch circle diameter. We represent by dp, pitch circle diameter, that is 260 mm. So we are to also have the shear, that is going to be, we have 100 Newton millimeter square, and we also have the power given, our P, that is 314 kilowatts. N, which is number of revolution, that is 500 RPM. What are we supposed to look for? We are to look for the diameter of the bolt. Let's write the D of the bolt. We are looking at them. So straight away, since the shaft is coupled with those bolts, what are we thinking? What we are looking here is that we want to look at the twisting of the shaft. Since we are given power, we are given number of revolution, we can derive the torque that this shaft is inducing in the bolt, right? Remember, the bolts are fixed on the shaft. So whatever twisting, whatever torsion is applied to the shaft is going to be induced in the bolt, right? So from the power equation, which says we have our 2 pi n on T divided by 60, we can find the torque, which is going to be 60 by the power transmitted 2 pi n. So here I can calculate my torque from the shaft, right? It is a torque from the shaft. So that is going to be 60 by the power transmitted, which is what? We have 314 kilo. Everything on 2 pi n. And our n is what? 500. So with this, our torque is going to be 5996.96. This is in terms of Newton meter because all the units are in their standard form. So if I still want to convert this to Newton millimeter, just multiply by what? 1000. So 996.96 to the power positive 3 Newton dot mm square or mm. We have this. Are we okay? So we now know the torque. Remember, if they are coupled, whatever torque is happening to the shaft is going to also happen towards the bolts, right? So we know the torque applied to the bolts. Now, what we have to also look for is we are going to look for the force because we are interested in finding diameter. We have to remember those shear stress is from the bolt, right? The shear they gave us is from the bolt, so everything that we are doing should relate to the bolt. But here we are able to deduce the torque from the shaft because they are coupled, right? The shear in the bolt may not be the same as the shear in the shaft, but the torque applied is going to be what? The same torque that is going to try to twist the bolt. So here, since we are relating to the bolt, we want to find an expression which will help us to deduce diameter from the bolt. So we have to apply that the torque in the bolt, which is the same as the torque in the shaft that we have, is going to be, we know that torque is force multiplying a certain radius. And we're giving the pitch circle diameter, the diameter passing through the center of all the bolts. So diameter divided by 2 is going to be radius, right? So this is going to help us calculate the force. From here, our force can be calculated as what? 2 times the torque on what? The diameter. And the force inside the bolt is going to be 2 times the same torque that we have. I'm working in millimeters. So this is going to be, you can also work in meters, 6.96 kilo. If you are working in the torque as meters, you have to also convert the diameter, the dp, to meters. So here I'm going to have 260 still in millimeters. So this is going to render my force F to be equal to 46130.46 Newton. So this is the force from the bolt. Are we okay? Yes, you have to understand from here that the torque applied is the force in the bolt multiplying by the radius, but the diameter was given. The diameter of what? The pitch circle, which passes through all the bolts. Alright, so now that we have a force and a shear, there's a relation between force shear for bolts. If you study machine design, there's this relation. So what we have is force resisted by bolts. So the force resisted by bolts is always given as F is, we have number of bolts, the shear multiplying the area. Do we get it? Yes. So this is an expression for bolts. If you want to relate the force to the shear, area, and number of bolts. So right from here, we can deduce something from that. Are we okay? So let's look at it. Now here we have our relation to be F is equal to, we have number, shear, and area. How many bolts were given? We have 6 of them, and the shear is also what? Given. That was 100. Now area of the bolt, we are going to consider a circular what? Cross section, which is pi on 4 multiplying d squared. We also know the force. The force, we calculated the force as 46130.46 equal to, that will be 6 by 100 pi on 4 the d squared. So this is the diameter of the bolt. All right, so here we can make d squared the subject, which is going to be the diameter of the both square, which is 4 multiplying the force, 46130.46. Then we divide through by our 6 by 100 by pi. And whatever you are going to get is going to be D, which is the diameter, is going to be 9.9 millimeters. Are we okay? So this, if you are designing a boat, 9.9 mm is approximately what? 10 mm or 10 millimeters. So we can say the diameter of the boat is what? 10 millimeters. Thank you for watching this episode. If you don't understand anything, please go back and try your hands on them. See you in the next episode.